So our topic of this class, our topic of this course is fuzzy logic in GIS. And we are going to discuss the following subjects. Today, I basically will give you an introduction and a motivation why fuzzy logic is important, or how fuzzy logic could be used in GIS. Then later we will discuss topics of membership functions, what operations on fuzzy sets are possible. We will discuss what's called linguistic variables and hedges. Just as an idea, what I mean with that is, if we, for example, say we are looking for a very steep slope, then this would be a value of a linguistic variable. The linguistic variable would be slope, and steep would be a value, and very would be a so-called hedge or a modifier. So very steep, how we can express these things in GIS and how we can use it for doing spatial analysis. We will also discuss fuzzy reasoning, meaning we are using rules and applying the rules to our data, we come to conclusions. So that is what we are going to discuss, let's say, in terms of theory. And then we will also discuss how we can create fuzzy sets in GIS. And in the end, we will do two case studies. Now, in terms of software, today I will use ArcGIS to show you some examples, to use perhaps QGIS, or I will show you both software packages. So if you do not have access to ArcGIS, you can also do the assignments or the exercises in QGIS. QGIS is freely available. You can download it and install it on your computers. So let us now jump to our introduction, where I will give you a motivation. What is fuzzy logic, or what are fuzzy sets, what means fuzziness, and how can we use that? But first, let me start with a, let's say, non-fuzzy example. Let's assume you have the following problem. You have a given data set with topographic data, and you should do a kind of site analysis where you have to find all areas that have a flat slope, a favorable aspect, a moderate elevation, that are close to some lake or reservoir, that are not near a major road, and that are not located in a park or some military installation. So what we see here is we have concepts that we use in our everyday language, in our everyday thinking and life. For example, flat slope. We do not say slope less than 10 degrees or something like that. We say flat slope. We say moderate elevation. So how can we express that? If we do not use fuzzy logic, the only way of doing that is to define classes with clear boundaries. And for example, to solve our problem, we could define the classes in such a way that we say flat slope is every slope that is less than 10 degrees. Aspect is favorable when the terrain is flat or it's oriented towards southeast, south, or southwest. Of course, this favorable aspect with the south, southwest, southeast orientation makes some sense on the northern hemisphere. On the southern hemisphere, it might be a different implementation of this criterion. Elevation is moderate. We say when it's between 1,500 and 2,000 meters. close to a lake or some water body means it should be within a buffer of 1,000 meters, and let's see, just not near a major road could mean that it has to be outside a buffer of 300 meters from the road. So that is how we would solve that problem in a GIS, for example. And in fact, I have prepared this problem in a GIS software, and in our particular case, I have prepared it in ArcGIS Pro. So don't worry if you don't have ArcGIS or ArcMap, just watch it here. We do not need this for the moment. So later on, I will provide you the data, and I will also, we will discuss how we can do that with QGIS. Now, this would be our base map. In fact, it's real data. It is data from one state in the United States, is Colorado, and the city of Boulder in Colorado. So if I, for example, take away the layers, here you can see that's the base map showing the city of Boulder in Colorado. What we have is we have an elevation model, a digital elevation model. We have lakes, we have parks, we have rivers, of course, and we have roads. So now we would like to implement our criterion, and we could do that, for example, using the model builder. For those of you who are familiar with ArcGIS, you know the model builder. It's basically the same in ArcMap and in ArcGIS Pro. So what you do is, in a graphic way, you solve your problem by linking together the data with some operations and the resulting maps. So what we do, for example, is we have our elevation model here. From the elevation model, we calculate slope and aspect. Then we implement our slope criterion, which basically says every slope less than 10 degrees is okay. So we give it a value of 1, and everything else is 0, which is meaning it's not okay. In terms of aspect, we can define our criteria in such a way that we say if it's flat, it's okay. And if it's between 135 and 225 degrees, it's 1. You know, aspect is here calculated in degrees from north. So north aspect would be 0 or 360. East would be 90, south is 180, west is 270, and everything in between up to 360. So we define our aspect criterion like this. We have the roads. So we have to select some major roads here. These are the major roads: the State Road 119, 793, and the US Interstate Road 36. This would be our major roads. Then from the roads, we calculate a distance raster, meaning we get a raster where every raster cell shows us the distance in meters from the road. And then we just define our criterion. We say everything in a distance from 0 to 300 meters is not okay, so we give it a value of 0, and everything more than 300 satisfies our criterion, not near a major road, so that gets a value of 1. And the same we can do with the lakes, the water bodies. So what we do is we are selecting our water bodies like lakes or ponds and reservoirs. Then we again calculate a distance raster, meaning creating a raster where every raster cell indicates the distance from the water body. And then we apply our criterion and saying everything within 0 and 1000 meters from the water body gets a 1, meaning it's okay, and everything else will get a 0. The same we do for the elevation criterion. We say everything between, or let's say everything up to 2000 is okay, and everything more than 2000 meter of elevation is not okay, and so on and so on. So in the end, we get rasters that we can overlay to calculate our final result, meaning what we have is everywhere where the criterion is satisfied, we will have a raster cell with a value of 1, and everywhere where the criterion is not okay, there will be a 0. So if we multiply all these rasters and there is only 1 0 for a cell, of course, this particular cell is not suitable. And where we have a 1 everywhere, the result will also be 1, giving us the final result of our problem here. By the way, I should mention here, when we look at this base map, you might have wondered about the elevation criterion. It's for some areas, it sounds pretty high when I say 1500 meters to 2000 meters. In fact, the city of Boulder itself lies at an elevation of 1600 meters. And to the west, we have the foothills of the Rocky Mountains here. And those elevations go up to 2,500 meters and more. So that's why we have this elevation criterion here. Now, again, jumping back to our model. Okay, that was the wrong model. This jumping back to this model. So what we do is I am going to run that model, and we will see what the result will be. So what is here now? So let me see, do we have... I just have to activate my lakes and roads again so that I can start my model. Okay, now everything is there. Now we can run our model. This might take now up to a minute or so. So all these different tools are now run, generating our output rasters, and in the end, we will end up with our final result, which will show us all those raster cells that satisfy all the criteria. And in a minute or so, you will see what the result is. So while this is running, again, this is meant to be a very simple example, showing you how you would do it without considering fuzzy logic. So you have to define clear class boundaries, like for the slope, 10 degrees of slope, and everything above 10 degrees is not good, everything below 10 is okay. And also with the distances from the road and the distances from the water bodies, we already see that, for example, if we have a slope of 10.1 degrees, it's not okay, but 9.9 or 10 is okay. Also, there is basically not much difference between these two slope values. Or we have a distance to a water body And let's say there we have a location that is 1,001 meter from the water body. It will be not okay. But if it's 999 meters, it is okay. And there is a 2 meter difference. So you could say, what's the difference here? But since we draw these clear boundaries, we have to exclude certain locations. And this is perhaps not the way how we normally would think. You just take 2 steps and you are in an area which is okay, and then you take another 2 steps and you are suddenly outside. So our model is nearly finishing. We are in the second to last processing step. Okay, this is the last step that's running now. It's combining all our resulting rasters. So only those where everywhere we have a 1 will be the final result. So just a moment until that is done. Still not completely done. Okay, now it's done. It took nearly 3 minutes. Okay, that might have also to do that. I have Zoom running and so on and so on. So let's go back. What we see here now is, let's say, what we have here, these locations here, these are all locations that are okay. So let me just, for a moment, take away all our background images and only keep the parks, the lakes here, the major roads. And what we see here, all these reddish areas, are those areas that are okay. So what we see here, these are water bodies here, so they're all close to water bodies. There's nothing near the major road because we said it can't be within a buffer of 300 meters from a major road. And so this is how we would do it when we use a GIS and we use these clear boundaries. Now, let me go back to our slides. So, okay, that's how we would do it. And that is basically what is our result. But now what we already saw is we say flat slope, we say moderate elevation, we say favorable aspect, we say near a water body or not near a major road. So these are concepts that are related to fuzziness. So fuzziness refers to vagueness or uncertainty, in particular in our human language and in our thinking. We already had some examples. Here I give you other examples. We say tall people. The concept of tall is vague or fuzzy. I mean, if you look at, for example, countries where people are in general very tall, for example, like the Netherlands, the people in the Netherlands are pretty tall. So if you have a height of 1.70 meters or 1.75 meters, you are definitely not a tall person in the Netherlands, because on average, most of the people are 1.80 meters or taller. But it's a vague concept. Or I'm looking, or my friends or people living close to my home. Close to my home is a fuzzy, a vague concept, which depends on how you define close, or areas that are very suitable for growing corn. What means suitable? It depends on many aspects. It depends on how you would model the concept of close or suitable or tall. So what we are doing here is, in this course, we will learn and see how we can represent these concepts and use these fuzzy concepts in doing spatial analysis. where we do not say yes or no, 0 or 1 or 0, and good and bad or something like that. No, we will have all these different grades that we usually also have in our thinking. And we will express these with a so-called membership degree, or a value of membership to which one particular element belongs to a fuzzy set. So when we go back, for example, to this first example here of tall people, we could, for example, then define our concept of tall. We will do that, you will see it later, we will do that with a so-called membership function. Then we take one particular person, look how tall that person is, and apply the height of that person to the membership function, and then we will get a value. And the value will be between 0 and 1. 0 means definitely does not belong to the class of tall persons. 1 would mean absolutely belongs to the class of tall persons. And in between, we can have any value between 0 and 1. So if you have 0.7 and you have 0.4 for a different person, then you know that the person with the membership value or the membership degree of 0.4 belongs to a lesser degree to the tall people than the person with a membership value of 0.7. And that is the whole concept of fuzzy sets. We can determine the degree of membership to a fuzzy set. I should say that the concept of fuzzy sets was developed in the 1960s out of the concept of fuzzy logic. So the foundation is fuzzy logic. Fuzzy logic means when we look at, let's say, the standard logic in mathematics or in logic theory, we have statements and we have truth values, and that can be true or false. If we look at fuzzy logic, we have exactly the same approach. We say some statement is not true or false, but it can have a truth value between 0 and 1, where 0 means false and 1 means absolutely true, and anything in between is a truth value that indicates the truth of that statement. So that was the foundation of fuzzy sets, and of course then from fuzzy logic, fuzzy sets developed, and we will deal here with fuzzy sets where we can determine for every element the degree of membership to such a fuzzy set. And as I already explained to you, the degree of membership will be given by a value between 0 and 1. Now, this slide shows you what's the difference between fuzziness and probability. You know that in probability theory, the probability is also given by a value of between 0 and 1, where 0 means not probable at all, and 1 means basically it will definitely happen, or it's absolutely probable. So the difference is that in probability theory, probability gives us an indication about something might happen, or the likelihood that an event will occur. Whether it's going to happen or not, we don't know. We can say, or the meteorological office can say, the probability of rain today is 60% or 0.6, but it might rain or it might not rain. We don't know. It depends on the development of the weather, but the probability is 0.6. On the contrary, when we talk about fuzziness, we talk about the degree of membership to a class. The class exists. Also, we have a certain, what we call universe of elements. And for every element, we can determine to which degree it belongs to the class. So there is nothing uncertain in terms of probable or probability. we have a class, and for every element, we can determine to which degree it belongs to that class. So, for example, the membership degree of myself to the class of young people is perhaps 0.2, depending on the definition, how we define young. Of course, I would enter my age in a membership function, and then I get a value. And let's say if I would be 20 or 25 years old, maybe the membership degree would be 0.9 or even 1. And when I enter a higher age, above 50 or 60, then the membership degree, of course, would be very low to the class of young people. So this is the major difference between probability and fuzziness, because people might ask, well, isn't fuzziness something like probability? Because we also indicated with values between 0 and 1. Yes, we do that, but there is a fundamental difference that in probability theory, we talk about likelihood that something is going to happen. We don't know where that's going to happen. Whereas in fuzzy logic or in fuzzy set theory, we determine the degree of membership to a class that exists. We define that class, and then we determine the degree of membership of some elements. Now, having explained that difference, let me just on that slide give you some mathematical notation that we will use throughout this course. Of course, it's a basic math that you are all familiar with. I just do it for the sake of completeness here. Well, if an element is a member of a set, we write it like this, meaning X is a member of set A or it belongs to A. If it does not belong to the set, we use that symbol. A is a subset of B, or A is included in B is used for that with that symbol. The union of A and B, the intersection of A and B, the complement of a set is indicated with that representation. And then this is a symbol from mathematical logic. It means for all elements, something is true, for example. So that would be some basic mathematical notation. And now we can already look at the definitions, what we have for crisp sets. Crisp means traditional sets, where we have a membership of yes or no, or 1 or 0, and then the fuzzy sets, where we have a membership that is between 0 and 1. So for traditional sets, let A be a subset of some universe, or sometimes it's called universe of discourse. Then the so-called characteristic function is defined as a function that has only values 0 or 1, where the value is 1 when the element belongs to the set, and it is 0 when the element does not belong to the set. So these characteristic functions gives us only a 0, 1, and false or true, not member or member information. If we take, for example, the universe being the set of all students in the world, and A as a subset of all the students in the world are the persons who attend this course, then the characteristic functions for every one of you would be 1, because you are attending this course, and some other student who is not attending this course would have a value of his or her characteristic function of 0, because that person is not attending the course. So we discussed the characteristic function for traditional sets. The characteristic function always giving us a value of 0 or 1, 0 when an element does not belong to the set, and 1 when the element belongs to the set. With fuzzy sets, we define a fuzzy set with a membership function. Again, we have a universe or universe of discourse, X, and a fuzzy set A is a fuzzy subset of that universe and defined by a membership function mu of A. The membership function is defined as a function that gives us values between 0 and 1, so in the interval of 0 and 1. And the function is defined according to the class that we want to model. So we will talk about membership functions very soon and what are which criteria a membership function must satisfy. There is just one simple statement: the universe or the universe of discourse is never fuzzy, because every element belongs to the universe. So on that slide, you see a summary. On the left-hand side, what is the characteristic function for traditional crisp sets? And on the right-hand side, you see the membership function defined for fuzzy sets. So the major thing here is the characteristic function only gives values 0 or 1, whereas the membership function gives us values in the interval between 0 and 1. Now, let's look at an example. In the introductory talk, I already used the concept of tall people. So we might have, let's say, the concept of height of a person or height of persons. And we define 3 classes: short, average, and tall. So short person, average height person, and tall persons. And how can we do that? And let's look at that example, taking 3 persons. Person A has a height of 185 centimeters, B 165, and C 186. So you already see here A and C are nearly the same height. There's only 1 centimeter difference. So if we use traditional sets, traditional classification, we might define these 3 classes in such a way that we say, okay, everyone up to 165 is short. Between 165 and 185 centimeters, the height is average, and above 185, it's tall. So when we now take our 3 persons, we see that A is exactly at the boundary, and B is at the boundary, and C is just 1 centimeter taller than A. So what we would do here is we would say, okay, C falls into the tall class, A might fall into the average class. If we say the class is closed to the upper boundary, then 185 would still mean average, and 165 would mean still short. So that's the traditional approach with very clear-cut boundaries, or clear class boundaries. If we use a fuzzy approach, we have to define membership functions for every of the class. So for short, we have to define a membership function. For average, we have to define a membership function. And for tall, we have to define a membership function that gives us suitable values for a particular height that we enter. So if we again have our 3 persons here, how could we define, for example, a membership function for short? Well, we could define it in such a way that we say, okay, it starts at 0 with, of course, nobody has a height of 0, but we just, in terms of mathematical function definition, we say from 0 up to something like 140 or so, or 150, it's definitely 1, and then the membership degree decreases till 175, something like that, or 180. So the taller a person gets, the lower the degree of membership to the class short. And then from this point on, for example, like A or C, they have a membership of 0 to the class short because they are just too tall. Whereas B has some degree of membership to the class short. In the same way, we would define a membership function for average. Now, we could say we take an average height, let's say something like 175. There, the membership to the class average height is 1. And the shorter someone gets, or the taller someone is, the less the degree, the membership degree to the class average height, which is logical. So if you have an average height, and that is, let's say, definitely 1, and then the shorter someone is, or the taller someone is, the less is the degree to the class average. And for tall, we could define such a membership function. So from 0 up to, let's say, 170, somebody is definitely not tall, meaning the membership value is 0. Then it increases, and let's say from 190 or something on, the degree of membership to tall is definitely 1 and remains 1. And here in between, we have an increasing degree of membership. So if we look now at our 3 persons, and let's look at the left-hand side where we are using the characteristic function, meaning we can only have a membership yes or no to a certain class. Then person A with a height of 185 will fall into the average class, because we said the class boundary is closed to the upper value. And of course, it will not be in the short or the tall class. Person B will fall into the short class, and person C will fall into the class tall. Now, A and C have nearly the same height. As you can see from the data, there's only 1 centimeter difference. So if they stand next to each other, you might not be able perhaps to distinguish that they have a different height, but yet in our classification here, A is average and C is tall. Now let's look at the fuzzy approach. When we use this fuzzy approach, we will get a degree of membership to every class. So for example, person A with a height of 185 has a degree of membership of 0 to the short class. This is the membership function for short, as you can see here. The person has a degree of membership of 0.6 to the average class and of 0.5 to the tall class. And B has a degree of membership of 0.5 to short and 0.6 to average. And C has a degree of membership of 0.56 to average and 0.53 to tall. So what you can see here from this table, that every person here has a degree of membership to each of these classes. of course, there are some classes where the person has a degree of membership of 0, meaning it definitely does not belong to that class. But there are 2 other classes where there are varying degrees of membership. So, for example, person A is rather average than tall, because it is 0.6 is a higher value than 0.5. Or person B is rather average than short, and person C is also rather average than tall. Also, there is nearly no difference. So what you can see from that is that the approach using fuzziness, using fuzzy sets defined by a membership function, gives us a much better way to express these vagueness or these transition zones from one class to the other. So in other words, the class boundaries are not sharp anymore. The class boundaries are in a way fuzzy and allow us to a much better degree to express that fuzziness, like in our example here, person A and C, that are nearly the same height, and we can see their membership to the classes average and tall. And in this case, so that C is rather a little bit more belonging to the average than to the tall class. So this is a very simple example showing you how we can express fuzzy sets using membership functions. And later on in the course, we will do exactly the same with geodata, where we can then express concepts like steep slope or flat slope or moderate elevation and things like that. And just as a brief note on that, we will always do it on raster data sets, because for rasters, we can apply a membership function for every single raster cell. So every raster cell has a value, take the slope. Every slope raster has a slope value for every single raster cell. And if we have a membership function, for example, flat slope, we can apply that function for every slope value for every individual raster cell. And in the end, we get another raster, which shows us only the membership degrees to the class of flat slope. So taking a raster representing some geodata, applying a membership function, we will get a fuzzy membership degree to that particular class, and it will be a raster that only has values between 0 and 1. 0 meaning does not belong to that class at all. 1 means belongs to that class, definitely, and anything in between is a degree of membership. Now, one more slide showing you how fuzzy sets are often denoted or written down in the literature. If we have a universe with members, elements x1 to xn, and that should be a finite fuzzy set A, then we can express this fuzzy set A by pairs of membership degree of a particular element. And we concatenate this using this plus symbol. So please note that this slash here is not a division operator, and this plus is not an addition operator. This slash only means it separates the membership value from the element to which it belongs, and the plus means only concatenating element with element, so listing all the elements. And even if we take a shorthand notation here with this sigma symbol, it is not a sum. So it is a notation that is often used in the literature about fuzzy sets. And admittedly, it can be confusing if you consider that to be a sum or this slash to be a division. So please, once again, this slash is not a division. The plus is not a sum. It is just a notation to indicate a membership value for a particular element and list it one after the other. So if you can basically write down all the elements of a fuzzy set, if it's a finite fuzzy set, of course, then you can write it down in such a way. This is just for explanation purposes. If you run across the literature on fuzzy sets, and you might find such a notation. So please don't be confused. It's not a sum and it's not a division. So let's now move on to some concepts of fuzzy sets. You all know, let's say, traditional set theory, where you know in traditional or the usual set theory, we have sets, we have elements, we have certain operators on sets, like I mentioned in the introduction. We can have a set union, intersection of sets, we have the complement of a set, we have the empty set, and so on. We also have these concepts in fuzzy sets. So the empty set in fuzzy sets is defined by for every element of the universe, the membership degree is 0. Then this is called an empty fuzzy set. And for every element of the universe, we have by triviality that every element belongs to the universe, meaning the membership degree of every element to the universe is 1, because as we said, the universe is never fuzzy. So these are just to complete our definitions and our motivation for fuzzy set theory. And by the way, the notation for empty set, you can find this symbol or you can find that symbol. So both symbols are okay, using or representing the empty set. Now, in the next chapter, we are discussing membership functions in a little bit more detail and what are the criteria for membership functions. We will see different types of membership functions, and we are going to define now what's a membership function. Now, as we already said, when we defined a fuzzy set, we said every fuzzy set is defined with a membership function, and the membership function gives us values in the interval between 0 and 1. So every membership function must be a real valued function, meaning it must produce real numbers, and those values must be between 0 and 1. They cannot be less than 0 or greater than 1. So they must be between 0 and 1. Of course, 1 it's not necessary that there must be a 0 or there must be a 1 as a membership value. But if there are values, then they always have to be in that range between 0 and 1. And a membership function should be defined in such a way that where the elements definitely belong to the fuzzy set, there the value should ideally be 1. So let's just recall our example here. Let me jump back to our example. If we, for example, define the concept of tall, a fuzzy set for tall, and we, let's say, have a population where we know that in the normal way of thinking, somebody is definitely tall when that person has a height of 180 centimeters or more, then of course the membership function for tall should be defined in such a way that anybody who has a height of 180 or more definitely receives a membership value of 1. So that is what I mean with this statement here, that the membership values should be 1 at the center of the set, meaning for those members that definitely belong to the set. Another condition is that then the membership values should fall off from the center in an appropriate way through the boundary. So when we again look at our example here, we defined in the crisp sets, we defined, for example, a height of 185 centimeters as being the boundary of our class between average and tall. So the 185 here is, perhaps I could, just checking. Need a pen here. So the 185, sorry, I missed a little bit. So anyway, here is our boundary, our crisp boundary. So meaning the membership values should, from our center of the set, which in our case of tall, for example, starts here from 100, let's say from 190 or so, everybody taller than 190 definitely is tall, and then it falls off and goes through the crisp boundary that we would define as the boundary for the crisp set at around 185. So what this statement here means, the function should then fall off from the center through the boundary, and the points with a membership value of 0.5, which is called also the crossover point. This crossover point should be normally at that area where we would draw the crisp boundary if we take the crisp classification, a clear cut boundary classification, like 185 in our example. We say the boundary between average and tall is 185. So the crossover point of our membership function for tall should be at 185, meaning if someone has a height of 185, the membership degree would be 0.5. Now, how do we choose a membership function? How do we define the membership function? By now, you should already have got some idea how we do that. We have a concept, a model, like tall people, like steep slope, like moderate elevation. So for our particular purpose, we have some concept, how we would define tall, how we would define flat slope, how we would define moderate elevation. So the membership function depends on the application. If we say moderate elevation, we saw in our example from the boulder area that moderate elevation there is an elevation between 1500 maybe and 2000 meters of elevation, because the city itself is already at an elevation of 1600 meters. But if we go to a different part of the world, let's say we go to the Netherlands, where we have areas that are below sea level, and the highest mountain or hill in the Netherlands is just 300 meters of elevation, then we would define moderate elevation, of course, completely different in that part of the world. So it pretty much depends on the problem at hand and, of course, on the knowledge, the expert knowledge, the modeling approach. So how would you normally define moderate elevation or steep slope or flat slope or tall person? And then you have to define the membership function according to that model, according to also your experience and your knowledge. So again, when we jump back to our introductory example, we said anything should be close to a lake. And when we say close, we mean anything within a 1 kilometer distance, or we said not near a major road, anything must be at least 300 meters from the major road. And that might be nonsense or it might be suitable, but it very much depends on the knowledge and on your modeling approach. Now let's look at different membership functions. First, I will introduce to you linear membership functions. This is the simplest way of defining membership functions. Then we will look at other possibilities like sinusoidal membership functions using trigonometric functions or Gaussian membership functions. They are called Gaussian functions because they resemble a bell shape as you know from probability theory. Now, the simplest membership function is the linear membership function. On the left-hand side, you see an illustration of a linear membership function. Linear means that the function consists of pieces or sections that are linear functions. Like here, we have one parameter here. In this particular example, it would be 20. So from 20 on, the function linearly increases till it reaches another parameter, b, which in our case here has the value of 40. Then it stays linear at 1 till it reaches another parameter, c, which in our case is 60. And then it falls off in a linear way till it reaches the fourth parameter, d, where it becomes 0, and from there on it remains 0. So this is the most general form of linear membership function, and on the right-hand side you see the mathematical expression using the 4 parameters a, b, c, and d. So once again, for every value less than a, the membership degree is 0. For every value between a and b, the membership value is x minus a divided by b minus a. B minus a is exactly the difference here between these two parameters. Then between b and c, that is this part here, the membership degree is 1. And then the membership degree falls between c and d according to the expression d minus x divided by d minus c. And for every value greater than d, which is this parameter here, the membership value again is 0. Now, this is the simplest way of defining a membership function. And in one of the next slides, I will show you how many different situations or models you can express using these type of function. Now, I also mentioned sinusoidal membership functions or a membership function that uses trigonometric functions. What does it give us? Well, it gives us a non-linear function. So you see, for example, this part of the membership function is not a straight line anymore. It's not linear. And also this right-hand part of the function here is not straight, it's not linear, it is a curved line, which allows us in a certain way to express some models where we do not want to have a linear approach. Now, what you see here is on the right-hand side, again, the mathematical expression, how to compute the values according to the different parameters. So again, for every value less than a, it's 0. Between a and b, meaning this is this ascending part here, the formula would be 1 divided by 2 times 1 minus cosine of pi x minus a divided by b minus a. For every value between b and c, it's 1. And for the descending part here between c and d, the formula can be expressed like this. And for every value greater than d, it is 0 again. Now, it can be easily proven or verified that for every one of these functions, the value can only be between 0 and 1. So there is no possibility here to receive membership values that are outside the interval of 0 and 1. Now, I mentioned before, with that type of general membership function, you can express many different concepts or models. And we will use the linear membership function to explain these different concepts. No, let's look at this. This is the most general form of the linear membership functions with the 4 parameters a, b, c, and d. It's also called a trapezoidal membership function because it resembles a trapezoid, as you can see here. And it basically is used for modeling classes that have increasing membership degrees between 2 parameters a and b. Then the membership degree stays 1 up to the parameter c, and then it decreases again until d, and there it remains 0. Now, if b and c are the same value, then we have what we call a triangular membership function. You remember we had this example of average height people where we had the membership degree of 1 at, let's say, the average height of our population, and the shorter someone gets, the lower the degree of membership, or the taller someone is, then also the lower the degree of membership. And then we look only at the left side of our membership function, meaning only the ascending part. So up to a certain parameter, it's 0, then it increases until 1, and from there on, it stays 1. This is called an S-shaped membership function because somehow this shape of the function resembles an S. And on the other hand, we could only look at the descending part of our membership function. We say up to parameter C, everything is 1. Then it decreases until parameter D, where it becomes 0. And from there on, it stays 0. This is called an L-shaped membership function because somehow it resembles the shape of an L. Now, looking at these 4 possibilities of using the general trapezoidal function, we can model the following situations. As I already said, if we have a kind of a mean value or a central value that represents some average or mean value, and from left to the and right, it falls off, we can represent situations or models like average height or moderate elevation, because with moderate elevation, we could, for example, say, well, between, let's say, 1,500 and 1,700 meters, the elevation is definitely moderate. There it should, the membership value should be 1. And then the lower the elevation, the less the membership degree to moderate, or the higher the elevation, also the less the degree to moderate elevation. So every situation or every model where we have some average or mean value where the membership degree is high, and the further you go away from that mean value in both directions, the less the degree of membership. Such situations can be modeled using a trapezoidal or a triangular membership function. An S-shaped membership function will be used in such situations where we say the higher the value of our elements, the higher the degree of membership should be. So if we go here to the right, the higher the value, also the higher the degree of membership. This is something like concepts, we could say, high elevation, steep slope. So the higher the slope value, the higher the degree of membership to steep slope. Or tall person, the taller the person, the higher the degree of membership to tall persons. So whenever increasing values of the elements result in higher membership degrees, we would use an S-shaped function. And on the contrary, if we say the higher the value of an element, the less the degree of membership, we would use an L-shaped membership function, something like short people. So the taller the person gets, the less the degree of membership to short people. Or flat slope. The higher the degree of, the higher the slope value, the less the membership value to flat slope. Then we would use an L-shaped function. And then, of course, we also have the, as I mentioned, the Gaussian membership function, which can be defined in such a way where we have parameters C and sigma, that where C is the kind of the mean value and sigma is a kind of span, where we can also express the same concepts like we would do with, for example, triangular or trapezoidal membership functions. So these are some examples of membership functions. There are many others that can be used, and later on, when we will look at the GIS implementation of fuzzy sets, we will see that every software, GIS software, has not every, I mean the ones that we are going to discuss, like ArcGIS or QGIS, they have functions for fuzzy sets, and they give you a range of 5 or 6 types of membership functions that can be used for defining fuzzy geosets. Now, this basically would bring me to towards the end of our class of today.